Hello. Today we are going to learn improper integrals. There are two types of improper integrals. The first type is infinite intervals. That's what we're going to learn today. In the next day, we are going to learn improper integrals with infinite discontinuity. Okay, that's type 2. Today we're going to learn type 1, which is improper integrals, uh, infinite intervals. All right. First of all, let me explain the format of the integral in this type. For that, I will give you the definition. The integral integration from a to b f of x dx is improper and has infinite interval if either a equals negative infinity or b equals positive infinity. All right, this is called type 1 improper integrals. Okay, this is type 1 improper integrals, which is infinite intervals. All right. Let's move to the first example so you can understand this very well. Example number 1. Integration from 1 to infinity 1 over x dx. Okay, here you see the upper limit is not a real number. This is not a real number. Okay, that is not a real number. So this is called an improper integral where you have infinite intervals. Okay, this is not a real number, so this is infinite. It is infinite. All right. So first of all, I'm going to give you the method. There's a method in this part. Let's learn the method. Method has 3 parts. First part of the method, if integration from a to t f of x dx exists for every number t greater than or equal to a, then integral from a to infinity f of x dx equals limit t goes to infinity a to t f of x dx. Okay, so this is the first case under the method. So let understand this. What I'm saying is, let's say you have to compute that. Here you have improper integral, which is infinite. That is infinite. That upper limit is infinite. Since it's infinite, you won't be able to integrate it. So what you would do, so you just replace this infinity by that t. Okay, t is not infinity, it is just a real number, and then you just integrate that with t. Okay, you integrate that part with t. Once you have integrated that, you send this t to infinity. Okay, you say t goes to infinity. It is technically similar to this. Okay, this part is technically similar to that, but the advantage is you do not integrate with infinity right there. Okay, so that is the first case. All right, so now go to the second case, B of the method. If the integration from t to b f of x dx exists for every number t smaller than or equal to b, then integration from negative infinity to b f of x dx equals limit t goes to infinity minus t to b f of x dx. All right, so here we use a similar type of trick. Here the trick is you have to integrate from negative infinity to b. So this is infinite. What you do is you just introduce minus t, rather integrating with negative infinity, you just introduce this t for infinity, and then we say t goes to infinity like before. All right, so that means technically this is same as that. This entire part is same as that. Then part C, if both integration from a to t f of x dt for t greater than or equal to a and integration from t to b f of x dx for t smaller than or equal to b exist, then integration from negative infinity to positive infinity f of x dx equals limit t goes to infinity integration from t to c f of x dx plus limit t goes to infinity c to t f of x dx. All right, so here in part C, what we have done is we used part 1 and part B. If part C is not something very new, what we have done is for the lower limit, we use that along with this. For the upper limit, we use that along with this. Okay, and then this C is new. This parameter C is new that we just introduced. All right. So C can be any number. C can be any number. Keep that in mind. All right. Now let's work on example number 1. I already gave you example number 1, which is integration from 1 to infinity 1 over x dx. All right. Now you see the here you have the infinite upper limit. So you go for case A. So this is the case that you are going to use. All right. So you write this to be, this equals limit t goes to infinity, integration from 1 to t 1 over x dx. All right. Now you just integrate this. Now this is simple integration. This part is simple. It doesn't have infinity. So you write this limit t goes to infinity. Integration of that one is ln x. Then you apply the limits 1 to t. And then this is limit t goes to infinity. And then this is ln t minus ln 1. You know ln 1 is 0, and this is limit t goes to infinity ln t. Okay, when t goes to infinity, ln t goes to infinity. So here the answer is infinity. Okay, let me draw a small sketch here. So this is the plot of ln, if you can't remember. This is ln t, this is t. All right, so that's example number 1. Okay, now I'm going to give you 2 other definitions. Let's learn 2 other definitions. These definitions are for convergent of an integral. The definition. The first definition, an improper integral is convergent if the limit exists. All right. Then next definition, an improper integral is divergent if the limit doesn't exist. Okay, it is improper integral, convergent if the limit exists, divergent if the limit does not exist. Okay, so consider example number 1. This was the given problem to you. Integration from 1 to infinity 1 over x dx. This was infinity. Alright. Now you see the limit does not exist. Okay, this means the limit, infinity means limit does not exist. Okay, so that is an improper integral. Thus, the limit does not exist. See, if the limit does not exist, that means it is divergent. Alright, so what I want to say is this limit divergent. Integration from 1 to infinity 1 over x dx is divergent. Alright, so let's consider example number 2. In example number 2, you have to integrate from negative infinity to 0 x times e to the power x. Alright. Here the lower limit is infinite. Lower limit is infinite. Now go back. It is actually case B. Alright, it is case B. So what you do is you just introduce limit. So you write this to be limit t goes to infinity minus t to 0 x ex dx. Alright, now it is simple integration. I'm writing limit t goes to infinity every time. So here what I'm doing is I'm using UV rule for integration by parts, if you can remember. Okay, integration by parts. So for that what I do, I have to find u and v. Alright, so integration by parts. Let me note it here from here to here. What I'm using is integration by parts. Alright, the formula is u times v prime equals uv. Let's say the limits are a b minus the limits are ab u prime v dx. I forgot to put dx here. Let me put that. This should be dx. Alright, so this is integration by parts. I'm going to use the same formula here. Okay, so you have to find u and v prime. Alright, so you could use u as x. Let me get this out. You could use u as x and v prime as ex. Then you have to get v out of v prime. That is v is integration of ex with respect to x. So that will give you v equals ex. So you know v, you know u. Okay. this is integration by parts. All right, now we're going to rewrite the problem. Problem is limit t goes to infinity. It should be minus t to 0. The first step is you just write this is u times v here. So u times v is x times e to the power x. Then you have to apply the limits. Minus t to 0 minus u prime v. Integration from t to 0. U prime is x prime, which is 1. This will give you u prime equals 1. And then v should be e to the power x dx. Alright, so that's easy now. Go forward. So this is limit t goes to infinity. So you just plug the upper limit, you get 0. You just plug the lower limit. It is minus t e to the power minus t. And then here, integration from minus t to 0 e to the power x dx. Alright, then this will be limit t goes to infinity, curly brackets, t e negative t. Here this minus, then integration of e to the power x is e to the power x. The limits are from negative t to 0. Alright, then simplify inside. This is limit t goes to infinity, t e to the power negative, t times e to the power negative t, and minus e to the power 0 minus e to the power negative t. Again, limit t goes to infinity, t e negative infinity, and then e to the power 0 is negative 1, and then this is positive e to the power negative t. Alright. Now I'm going to apply the limit. That means I can just write this as t goes to infinity. T e negative t, and then I just write minus 1, and then write plus limit t goes to infinity negative t. Okay. Now you should need to know the limits of functions. Okay, you should know limits of function. If I recall the shape of e to the power negative t, this is the shape of e to the power negative t. E to the power negative t. This is t. The shape should look like that. Alright, that means when t goes to infinity, e to the power negative t goes to 0. So the entire term goes to 0. And then you have to find that, okay, when t goes to 0, so this is something like 0, infinity times 0. Alright, it is something like infinity times 0. Infinity times 0 is undefined. It is undefined, you know that. There are some undefined forms. Infinity times 0 is undefined. Infinity to the power 0 is undefined. 1 over 0 is undefined. There are several undefined cases. So this is one of them. This is an undefined case. Because of that reason, we have to use the Hopital's rule. If you can remember, Hopital's rule that you learn in Calculus 1, that's what we're going to learn here. Alright, so before going to Hopital's rule, let me polish this little bit. So here you get this equals limit t goes to infinity, that minus 1. Let me take this as a. Alright. Let me write. We use Hopital's rule Hopital's rule for A. Okay, you have learned this in Calc 1. In Hopital's rule, what do you do? If you have an indeterminate form, this is A is in indeterminate form. If you just apply the limit t goes to infinity, t e negative t. If you apply the limit, you will get infinity times 0. This is indeterminate. This is indeterminate, all right? So then you have to use the Hopital's rule. Thus, use the Hopital's rule. In Hopital's rule, what do? You rewrite this function as limit t goes to infinity. You rewrite it as a quotient t over e to the power t, and then you differentiate the numerator and the denominator separately. Okay, so you write dt over dt and then det over dt. You integrate. What I'm saying is you differentiate the denominator and numerator. All right. So then this equals limit t goes to infinity 1 over e to the power t. Now you apply the limit. What you get here is 1 over infinity, which is 0. All right. So that part is 0. Thus, by Hopital's rule, that integral, which is not the integral, I mean the limit t goes to infinity t times e to the power negative t equals 0. All right. So now let me put equation number 1. Let me denote this as equation number 1. By 1, what I write is the given integral, which is x times e to the power x, which is this is a is 0, 0 minus 1 equals minus 1. All right, that is the answer, which is finite. Okay, this is finite. That means exist. It is exist. That since it is exist, go back to the definition where you learn divergence. The limit exists, then it is. Limit exists. This is the case. Limit exists. Now the integral is convergent. Okay, you say the integral is convergent. That is the integral xe to the power x dx is convergent. All right, so we discussed 2 examples. In the first example, we recognized that the integral is divergent because you got infinity. So it was divergent. In the second case, it was convergent. That's because you got just -1. All right, it was convergent. So that's it for this part. Next day we are going to learn improper integrals with infinite discontinuity. Thank you very much.